identification of weak molecular absorption in single wavelength SNOM images, but basically it's about the negative phase contrast you can see in some SNOM images. So just a quick reminder what you already heard today in a lot of talks and also yesterday, that if we have a dielectric material, for example, a polymer or a biological sample, then normally the near field amplitude basically reveals the local reflectivity of our sample, and the near field phase reveals the local absorption. And it's defined in a way that when we have an absorbing material, then we should have a positive phase contrast relative to a non-absorbing reference sample. So this is what you see here, for example. So this is PMMA absorbing on a silicon substrate. And basically, if you have a non-absorbing material, the phase should be 0 in contrast, again, to your reference sample. But what you sometimes observe is what you see here, so this bluish area is a negative phase. And the question is, what does this mean? Because in principle, the phase should be 0 or higher than 0. So actually, this is a phenomenon which is observed quite often. So these are two examples from literature. And here, for example, you have a purple membrane on a silicon substrate, and you can see that this is darker here compared to the silicon substrate, so this means we have a lower phase, so basically a negative phase compared to our substrate. And also this is a second example here, so here is an image, some phase images for different wavelengths, and you can see here, for example, the material is absorbing, but then you go here, and again you see that the phase is lower compared to the gold substrate in this case, so also here you have a negative phase. So this is really an effect which is observed quite often, and the question is why? So where does it come from? So we also prepared a sample of PMMA and polystyrene on top of a silicon substrate, and you can see here the height of the two films is roughly about 50 nanometers. And then we looked at the nano-FTIR spectra, and you can see that the PMMA here has this very prominent peak around 1,735 inverse centimeters. And what we did now is we were using different wavelengths to take SNOM images. So one here in the region of the peak, but also here in the region where the PMMA is non-absorbing. And this is basically what you can see here. So at 1,735 inverse centimeters, we have the strong PMMA absorption here, so this is indicating in red. So in all the images I'm going to show you today, a red color means that we have a positive phase contrast to our substrate, which should always be whitish because there the phase is 0. And then a blue color means that we have a negative phase contrast. Okay, so for the PMMA, we see here where it's absorbing, we have this positive phase, but then we go to the region where PMMA is non-absorbing, and you can see here this bluish color. This means we have a negative phase here, and this is what you can also see in the line profiles down here. On the other hand, we have here polystyrene, and polystyrene is in this investigated wavelength range always non-absorbing, and you can see here that we always have the slight negative phase contrast. So in all the cases, we have here this negative phase of about -5 degrees, and where the PMMA is absorbing, we see this positive phase of 55 degrees. One thing I want to mention is that this negative phase is not because we are doing something, let's say, wrong in our measurement. So you can also have a negative phase if your mirror is basically going in the wrong direction, but this you can directly see when you start this PS head, so you might remember from the talk Martin gave yesterday. So this here is a phase sweep for adjusting the mirror amplitude when you try to disentangle phase and amplitude signals. And what you can see is that this is the convention, so you start the sweep, then you should see this drop, and then you have the mirror movement, and this then yields to an absorption, yields then to a positive phase contrast. And when you see this jump up here, and then you have this sweep, then this reveals a negative phase contrast for absorption, but this is basically, you can avoid that by looking on how your phase is behaving. So this is not what I'm going to talk about. We are really, let's say, in the correct condition here, where absorption yields a positive phase, but still we can observe this negative phase contrast. So what we did is we took a series of images with different wavelengths along this PMMA absorption peak, and we were determining the phase on the PMMA in comparison to the substrate. And this is what you can see here. And you can clearly see that in the region where the PMMA is not absorbing, we have this negative baseline, and then the PMMA starts absorbing, and we get this positive phase values. We then compared this extracted phase spectra with a nano-FTR measurement, and this is a nano-FTR measurement with the peak here. And what you can see is that here we always have positive values, and this is because normally we do this baseline correction, and this baseline correction we apply to get rid of the interferometer drift. This automatically also rules the phase contrast. And if you now compare your nano-FTR measurement with your extracted phase values from the SNOM measurements, what you can see is that they basically not fit very well together here in this range. So if you want to compare your nano-FTR spectra with your SNOM images, you will always have a mismatch of the values. So actually, you can also see the negative phase contrast in a nano-FTR measurement if you do the measurement so fast after the reference measurement that you do not need to apply this phase corrections. And then you can see that also in the nano-FTR measurement, basically we have this negative phase values, and if you compare that now to your SNOM measurement, you see that they fit very nicely together here now. So this negative phase contrast appears as well in nano-FTR as also in SNOM, but in nano-FTR you normally don't see it because you directly correct it with the baseline correction. Okay, so by now we know that the effect is there, that we see it, but still it's a question, where does it come from? And in order to investigate this effect, what we did is we prepared a sample of HBN on top of gold. And the HBN has a thickness of 90 nanometers, and we imaged it at a wavelength where it's also non-absorbing. So you will always find my measurement parameters down here for all the measurements I did. And what you can clearly see here, so this is the phase image. As I said, negative values are always blue. And you can clearly see in the line profile this negative phase contrast of minus 18 degrees. So it's a very strong effect here. So this shows that it's not only an effect which appears on organic materials, but also on non-organic materials, as this HBN flakes, for example. So our first thought was, okay, maybe it's a topography effect. Maybe it's because we go up with, so we move the tip down because we have a sample height, right? So what we did in order to investigate that is we additionally evaporated a 50 nanometer layer of gold on the sample. So basically, the step height here is the same as before, but now we go from gold to gold. And what you can see here, so now here in the phase image, you see that you do not have this negative phase contrast anymore. What you see instead is this small positive phase contrast. And actually, this is because now the topography is changing, and this is because the reflection phase increases. So this is basically a contrary effect to the negative phase contrast we observed. So, but it could still be some indirect illumination artifact. And well, I hope you remembered from the last talk that we can get rid of this indirect illumination artifacts by looking at the ratios of the higher harmonics. So for the phase, this means we have to take the difference. So what I did now here, so these are the two images from before, and now I calculated the phase difference of the fourth and third harmonic. And what you see here in the case of the gold evaporated sample is that this phase artifact we see here, it's completely vanishing after taking the ratio. So this effect here really is an indirect illumination effect. Now, we can do the same for the uncoated gold sample, and what you can see here is that this negative phase remains. So this shows us that this effect really is a near-field effect, and it's not induced by some indirect illumination artifacts. So in order to see now a little bit more in detail what is going on, we took some retraction curves on gold and on HBN. And here I defined the height 0 as the first contact between the tip and the sample. And then basically you move the sample away. This is then the height. This is the distance between the sample and the tip. and all the data is normalized to the value on gold on first contact, so for H is 0. So this is the measurement. What you can see is, so this is the amplitude, that we have this strong drop of the amplitude within a few tens of nanometers. So this shows that our measurement really is background-free. And what you can see is that the amplitude we have on the HBN is much lower than the one we have on gold, because it's not so reflecting in this wavelength. Now we can look at the phase. And what you can see here in the starting region, where we still have a lot of near-field signal, what you can see is, so the blue curve is the phase on gold. You see that it's dropping here by a few degrees. If you look at the phase on HBN, you see that it's basically constant. So we reproduced the approach curves with the finite dipole model. And here I'm giving you some parameters if you're interested in that. And what you can see is that, so these are now the lines here, that we can really nicely reproduce the amplitude and also the phase here with the finite dipole model. And you can also nicely reproduce here the drop of the phase within the nanometers. So with the help of the model, we can have a little bit a closer look what's going on. So you already heard about this empirical parameter G, which was introduced to account for the radiative losses of the tip. And the calculations were done with this parameter here, which is typically used. And it goes into these parameters here when you calculate your polarizability, as you can see here. What you can then also do, you can just get rid of the imaginary part of this factor, and then you see that now the phase you are calculating is constant. So this means that this negative phase somehow comes from this part here, which is was introduced to cause for this radiative and eventually also dissipative losses of the tip. So basically, what's happening is, if you now look, let's say, from the right to the left, is you approach with the tip your sample, and this increases your near-field interaction. But this also increases the polarizability of the tip, and you will get larger radiative losses and also dissipation. And then what you have is this positive phase shift if you go close to the surface. And this effect is much stronger on gold than on HBN, because you just have much more signal, basically. Okay, so now we have understood where this negative phase is coming from, but of course we want to get rid of that in our images, because it's hindering us to identify weak molecular absorption, for example. So one correction method, which is working for the spectra here, is basically quite easy. So you measure SNOM images at different wave numbers, and you make sure that you're also measuring in a region where your sample is non-absorbing. And then you extract the phase values from each image, and you get this dots here, where you can see the negative phase. You can then just determine the baseline you have here, which is a -5 degrees, and then you can add this -5 degrees to all of your values, and if you do so, you end up with this curve here, which is now nicely fitting to your nano-FTR spectra and do not have any negative phase values anymore. So this is basically the first method you can do. But now we already learned that basically the negative phase contrast appears because we are referencing to a highly reflective substrate. So you could think of using a different substrate to normalize to. So in our case, we have here this polystyrene, which is non-absorbing in the whole range we are investigating. So you can see here that the negative phase is always roughly -5 degrees. And you can now use this one as a reference to your material you are interested in. So if you do so, you will also end up with a curve like this. Again, you see that you nicely match your nano-FTR spectra, and you do not have any negative phase values anymore. I want to mention that here you have to be a bit careful, because you have to use as a reference now also a non-absorbing material, which a similar thickness and also a similar refractive index as the material you are investigating, because otherwise you will end up again with subjective values, for example. Then you can also correct images, so not only spectra. So what you can do here is you take an image in a region where you know that your material is non-absorbing, and you normalize it to your substrate, as you always do. And then you take your series of images in the region you are interested in. So these are the uncorrected images. Each one, again, is referenced to the substrate. And what you can do now is you can switch here from all the other images. And this is what you get. And now here, for example, you see that at 1710 inverse centimeter, in the uncorrected image, it seems like that the PMR is non-absorbing here. But if you look closely now in the corrected image, you see that you have a weak absorption already at this wavelength. Again, you can now extract the phase spectra, and it fits very well to the nano-FTR here again. So basically, this is already more or less the whole story, but there's one thing I want to mention before I summarize. So this negative phase contrast is thickness dependent. So what you can see is that for very thick flakes of HBN, we have a constant negative phase contrast. But the thinner the flake gets, basically the lesser the negative phase contrast gets, and this is because you are probing more from your substrate, so from the gold below, and then the phase difference is not as strong as before. So this is what you also have to keep in mind. So with this, let me summarize. We have the negative phase. It occurs if you have a non-absorbing material on a highly reflective substrate. It depends on the thickness, the reference material, the tip you're using, your measurement parameters, for example, the set point and the tapling amplitude, and maybe even more. So I think here we really need to explore that a bit further. It originates from higher radiation losses and maybe also distribution of the tip on highly reflecting substrates. And you can correct it by subtracting the negative baseline, by referencing on a non-absorbing material, or by, for example, subtracting the reference image. And with this, I'm at the end.
Thank you. So the trick is to look at the signals, right? I mean, not unbalance too much with respect to what the material you are interested, right? And also that in principle, especially the referencing to a non-absorbing material, you can have a different sample, right? I mean, it must not be on the same exact sample. So.
Well, I would say it's better if you have it on the same sample, because as soon as you change some measurement parameters, it will also influence the negative phase. Yeah. So it's really depending on a lot of things. So if you want to use a different reference, also if you take a reference image, you should make sure that you take all the images with the same parameters, with the same tip on the same day. So make everything as the same as possible.
Yeah, one next to the other.
Yeah.
On the same scan.
Exactly.
Other questions?
Thank you for the nice talk. I have a question regarding this subtracting reference image. Don't you create other kind of artifacts when you do this, or other kind of artifacts?
Yeah, I mean, you have to make sure that you overlap the images. So if you make the first image and then maybe you have some drift and you took another image. So what I did in order to do so, I was making some kind of correlation. So I wrote myself a program where I could say, okay, I have this point in the image, and this should be the same point as the other point in this other image, and then you could see the overlap region. Of course, if you have some drifts, this could lead to some artifacts if you are looking at very tiny structures, for example. But here we have this big region, actually. So maybe you create some artifacts here or here, but in this case, it's not disturbing.
You did it in MATLAB, or which?
I did it with Python. But I think you can also do it with this, not with Origin, with Gwydion. You can also, I think so.
Any other question? If not, let's then.
There's one.
Thanks for the talk. I just wanted to make sure where last touch on taking ratios as self-normalization, and you touched on that. Then you said referencing to highly reflective sample. So how do we decide which approach to take if a self-normalization will render the need of taking reference spectra entirely? So how do we go about what measurements to take?
Well, I think I think this is something you have to decide from experiment to experiment. So if you are able to get rid of that, for example, I mean, the easiest method is basically just subtracting a baseline, right? So if you are sure that you have a region and you know that your sample is non-absorbing at that wavelength, you just take an image at that wavelength and calculate there the negative phase value you have, and then you just add this value to all the other measurements you do.
So it's a matter of selection, which one to kind of like use, or can I use both? For instance, taking ratios, then normalizing to reference, say, gold or silicon?
I mean, if you take the ratios, you will always get rid of the indirect illumination, right? So you can first take the ratio to get rid of the indirect illumination, and then if you still have some negative phase, you can think of doing another correction method to get rid of the negative phase, because this will not vanish if you do the ratio.
Right. Thank you.
Any other question? Comment? If not, let's thank Iris again.